Okay, welcome back from the break. So for the last lecture of today, we're going to be hearing from Julio Parra Martinez, who is at the Institute for, well, sorry, I promised myself I wouldn't even try to do it. So IHES, which is the French equivalent of the Institute for Advanced Study. And we gave Julio the challenge of tackling two really important techniques that are used in modern particle theory, scattering amplitudes and effective field theories. So please take it away.
Okay, thanks a lot. And also thanks for the invitation to lecture here. I'm actually very excited. Years ago, I was sitting there in 2019, and it was a great time. I met a lot of people that I'm still friends with, and actually, I even, conversations over lunch led to 2 papers with one of the lecturers. Wink, wink. It was also a formal TASI, and okay, I'm an amplitudes person. Depends who you ask. We are more informal or pheno, and okay, there's by one definition, phenomenologist is someone who cares about experiments. By that definition, I'm a phenomenologist. But if your definition is it's someone that calculates things with units, then I'm not a phenomenologist. So as Jesse was saying, I'm tasked with tackling these 2 subjects at once, and of that, I'm going to follow a slightly unconventional approach.
Sorry to interrupt, but that's the one that's cutting out.
Okay. Okay, but throughout, I'm going to be throwing a bunch of problems or exercises to you. So let's just start with one. So this is the first exercise. Complete the sentence. So the sentence is EFT is just ... Okay, so I want to hear different endings for this sentence from different people.
Amazing.
Amazing. Okay, I think we can all agree on that.
All field theory.
All field theory. Okay, more. So you can use just. Okay, let me give the definition that I will try to advocate in these lectures. EFT is just fancy dimensional analysis. Okay, or also dimensional analysis on steroids or something like that. And actually, to explain in which sense this is actually true and also somehow deep. Okay, and so I'll try to. EFT is what happens when you just put dimensional analysis together with the basic principles of field theory. Okay, so and I want to explain is EFT equals dimensional analysis plus the following things. Causality, unitarity, and symmetry. Okay, so all right, we all know this, but many times we take this for granted, that there's these principles that underlie all of our theories of particle physics and many other things. So I want to explain how these are extremely constraining principles that when you put them together with dimensional analysis, they just give everything we know about effective field theory. And we're going to do this by example. Okay. So we'll do this by example.
Are you in specific order?
No, I mean, it's a sum, so it's commutative. But I will be presenting them in some order. Yeah. But yeah, they're all equally important as far as I'm concerned. But yeah, we'll do this by example by focusing on amplitudes. Okay, so what is a scattering amplitude? We have some process in, out, This is 1 plus some quantity, A, which is our scattering amplitude. And okay, EFT perhaps is a bit more general because EFTs, they work for theories, like conformal field theories or phase transitions, critical systems, the statistical mechanics. Right here, we're going to think about particles and how they scatter. We're also going to think about them in relativistic quantum field theory, if only because it's easier to do dimensional analysis. The fact that there's a fundamental speed, the speed of light, and h bar, means that we can identify momentum and energies, time and space, and also energies and time and space and momentum. Okay, so there's only one size, one scale that we need to track, which is basically energies, and that will make our life easier. Okay. Now, there's already great lectures about scattering amplitudes and effect theory separately. So I listed there some of the ones that I like. So I encourage you to look at those. I'll also be putting some specific papers in this Google Drive that you might read with more details about some of the things I'm going to discuss. Okay. And the outline is going to be the following. So today, I'm just going to discuss all of these basic principles in detail. Okay, so there's going to be a fair bit of handwork, just like intuition and trying to understand at least what they tell us about amplitudes. But we already will get some concrete statements. Then tomorrow, we'll actually compute amplitudes by enforcing these principles again. So we'll see that we can just guess the answer. So I literally want you to think about these lectures as what you do as an undergrad when you figure out, say, the speed of sound on a string. If you know the mass and the tension, you can just figure out the formula. We're going to kind of take that approach, this kind of bootstrappy approach, where we're just going to impose all of these principles and see what the object has to look like. Okay. Then the next day, I'll talk about RG, or like running and matching. And this perhaps will be the most unconventional because typically I'll try to stay away from Lagrangians, operators, all of these things, because they're bad, but because I can, and because I think thinking about this directly for the amplitude kind of illuminates how all of this machinery that we usually use really follows from these principles. And then on the last day, I will try to, there's something that we call naive dimensional analysis, which is when we try to estimate the size of some of the coefficients that appear in the ansatz that we write for an amplitude, which is what we're going to be doing. So I will explain how we can remove the naive, how we actually can say something concrete about the size of these coefficients, again, based on these principles. Okay, so I think it's a useful exercise to do these things because, first of all, we'll see how this directly constrain a physical quantity. As I said, many times we take these things for granted. We just write a Lagrangian, we start to compute, and many of these things become kind of automatic. But by doing it this way, for instance, we can also avoid some technicalities. I will never talk about gauge symmetry because I don't have to. And also I can avoid things like field redefinitions, many subtleties that appear when you actually try to compute things with a Lagrangian, where you're trying to classify all possible operators. All of these things can be avoided because scattering amplitudes are both gauge invariant and invariant under field redefinitions. Okay, so field redefinitions is whatever choice of variables I make in the path integral. And also, it's a useful excuse to introduce a bunch of these amplitudes machinery to do computations that then you can just use to do your favorite computations. Okay, any questions about the setup? Okay, so let's do a similar exercise where we just go over these principles and we just say in words what they are. So, okay, what did I write first? Locality. Okay, so what is locality? Locality is the fact that interactions happen locally in space-time. Or at a point in space-time. Okay, causality. what is this? So cause precedes effect. Or in our relativity theory, also we have that space-like measurements commute. Okay, unitarity. What is unitarity? Probabilities are up to 1. Okay, and symmetry, okay, we all know what symmetry is. I'll be focusing on space-time symmetry, Poincare symmetry in particular. There's a lot I could say about global symmetries, but I won't have time, but I'm happy to discuss kind of how global symmetries appear in scattering amplitudes, how they manifest themselves in broken or unbroken. And as I said, I won't be talking about gauge symmetry. Okay, so actually I'll start with symmetry. And a lot of the things I'm going to say, it's going to be basically a review of things that you might have read in your textbooks, maybe Weinberg chapter 2 or in some chapter of Pescinus Roeder. But I think it's useful to review, and I'll put it in the context of amplitudes. So okay. So I'm going to think about scattering amplitudes in some theory with Poincare symmetry. So I have translations and rotations. So the algebra schematically looks something like this. So I have some momentum generators that commute. I have this transform as a vector. And then I have a bunch of rotation generators that satisfy the usual kind of commutation relations for rotation. So if we think about particles, which is what we want to think about for scattering, what is a particle? So there's this kind of fancy definition of a particle, which is an irrep of Poincare algebra. Okay, so it has a bunch of labels. Okay. So it's going to have something like a mass. So something that satisfies p squared equals m squared. So I'm going to label my particles, my states, in terms of some momentum variable, because then I can diagonalize part of this algebra. I can just choose eigenstates of p, which make my life easier because all of these commute. And then there's also spin. This is a bit more complicated. There's some like Pauli-Livansky vector, which is something like epsilon something like this. And then I have that omega squared equals m squared s plus 1. Okay, so these are the two Casimirs of this algebra. So these are the labels that I use. In my states, they will look something like something labeled by a momentum, and then there will be some other labels that in particular they will tell me how this thing transforms under Lorentz transformations. Okay. So how do we think about this spin or these extra labels? So there's this key idea that we're going to use to great effect, which is called the little group. How many people have seen all of this, by the way? Okay, so I'll go pretty fast, since I want to get to the fun stuff. Okay, so this little group is, there's some particular Lorentz transformations that leave my momentum invariant. Okay, so you can put labels, right? And in general, these states, these particles, will transform under some representation of the little group. So I have some unitary operation that acts on this. Then there will be some matrix, some representation rho of this little group that in general is going to mix these guys, and this little group is actually different for massive and massless particles. So for massive, it's very easy to understand. Okay, so for a massive particle, we can go to the rest frame. So we just have the mass, and then 0. And then it's easy to see that the little group is SO3, which is basically SU2. And you can think of it as in the rest frame of the particle, I can just do any rotation around the particle, and that respects the fact that it's stationary there. Okay. Okay, so in general, so matrix in this SU2 language will look something like this. Constant identity plus, so this is some cosine of some angle, this is a sine of some angle, and there will be some direction times some Pauli matrices. Okay, so you can think of this vector n, and then there's some angle here that appears in the sine and the cosine. Okay, and what are the irreps of SU2? So it's just like some symmetric tensor with like S columns, right? So my massive states will be labeled by a bunch of indices, SU2 indices, I1, I2S, where these are just SU2 index, and this thing is fully symmetric and traceless in all of these indices. Okay, so this is a massive particle, as far as I'm concerned, and when I compute scattering amplitudes, it will be overlaps between multi-particle states, which look like this. Okay. Massless case, which is a bit more interesting. What does the momentum massless particle look like? Okay, so the best thing I can do is just align it around the z-axis, so it's going to look like this. Okay, so what is the set of Lorentz transformations that leave this invariant? So there's a pretty obvious SO2 rotation, right? If I just do a rotation in the xy plane, this clearly leaves this invariant. So there's an SO2 or some U1. So let me call an element of this T, some e to the I theta, where this theta is just some rotation in the xy plane. And then when I act with my state on my states, then this thing will just be some power of this phase. Okay, so this is just going to rephase my states. And this weight here is that's what we call the helicity particle. Okay, so actually a representation is labeled by helicity, which is a half integer. Okay, instead of this SU2 representation here, okay, we can put this helicity label. And that's what we care about. Okay. All right, let me give you a couple of exercises if you want to have fun. So the first one is if you go to this Pauli-Lubansky vector, you can show that this thing also tells you about the helicity. So if you act on a one particle state, you can show that this is simply this. Okay, and then the other exercise is actually there's two extra Lorentz transformations that leave this invariant. So there are two boosts. that leave this momentum invariant, okay, just find them. Okay, I'm not going to say much about this, guys, because as it turns out that if you try to add labels so if you try to make this state transform non-trivially under this, so look at a representation that has non-trivial charges under these guys, turns out that this is something called a continuous spin representation, which has been seen as an oddity over the years. There's actually some people, there's the group at Slack, looking at whether these things actually make any sense as particles and trying to compute their amplitudes. Okay, I can tell you more about this over lunch if you're interested. But okay, at least for fun, you can try to find what these generators are. But for my lectures, I'll just talk about things, massless particles that have some fixed helicity. Okay? Okay, so in general, which is basically like two translations, and actually these two act on the translation. Translations in the xy plane, or like the boost, and then this SO2. Any questions about this? Okay, so key statement that I want to extract from all of this that we will use later after we discuss some of the other principles is the following. So because amplitudes are overlap between multi-particle states, they're actually not Lorentz invariant. They transform under this little group. Okay, so amplitudes are basically maybe some overlap between like P1, H1, Pn, Hn, and then okay, maybe K, then Pk plus 1, K plus 1, the dot, and Hn. So these things. Okay, so this is obscured when we write amplitudes in terms of polarization vectors and all of that. I will explain tomorrow how the polarization vectors arise. They're actually pretty weird objects because they transform both under normal Lorentz transformations and these little group transformations. So we'll avoid them as much as possible. But the amplitudes, they actually have to transform. And because they have to transform, we'll be able to use this to constrain their form. Okay, so apart from this, basically, to say this is that we just have that amplitude-dependent piece and some representation of the little group. All right. Okay. More on this later. Okay, let's move on to the second principle. So actually, I'm not following the order in which I wrote them. Okay, the second one is causality. So we said causality is the fact that kind of causal measurements make sense, that the kind of response to some action that you make on a system has to come after, right? And in relativistic theory, we can think of just a light cone. So this is the time direction. These are the space directions. And then I could insert a probe here, some source, at some point x, and actually ask if there can be a response at some point y. For instance, here, they're space-like separated. Right? Let me label this by tx. This is t prime x. Okay? And the claim is that a causal measurement vanishes. Let me write it. if t prime is less than t, and or these guys are space-like. Okay, so if I have some function measurement that depends on t prime minus t and yx, so I'm assuming translation invariance, so I'm just writing the differences. And I look at the plane where this is this delta t, which is t prime minus t. This is delta x, which is y minus x. This thing is only non-zero in the future light. OK, why am I talking about this if I care about scattering amplitudes? Scattering amplitudes are basically written in momentum space, so they're Fourier transforms of maybe some correlation function. But in any case, they should respect causality. So what do I learn about the momentum space representation of this thing? So let me first just take the, OK, let me just consider the Fourier transform. So I have m of some frequency and some momentum. OK, and now there's something cute that happens. For instance, let's just think about the Fourier transform over time first, while we're fixing this. Right? I told you that this function for delta t negative, it vanishes. So even though initially the Fourier transform goes from minus infinity to plus infinity, because this thing is 0 when delta t is negative, I can actually cut it off. And what does that mean? Actually means that this Fourier transform is defined even for imaginary values of this omega. So if I give this a positive imaginary part, right? If I write omega e plus if, right? Actually, the bigger I make f, the better defined this Fourier transform is, because I'm just going to add some exponentially suppressed factor, right? So e to the I omega delta t will be OK, and more generally, there's some cone over momentum space where you can extend this Fourier transform, right? So there's something. If I write omega and p in a 4 vector, right? Whenever q mu delta x mu is positive, where delta mu is in the future light cone, and q, so I'm writing p as s plus iq. So I can give both to energy and momentum some imaginary part q. As long as I choose this inner product is positive, then this thing is well defined. Okay. Which means that causal observables and in particular amplitudes are complex functions. Okay, so they're defined over complex momentum. The actual physical value of the amplitude is the boundary value, is when we actually set this p to be real, of course. But they make sense somewhere out in the complex plane. Because of that, we'll consider scattering for like generic complex momenta. And then there's also something else that we learned. So typically, this is called analyticity of the scattering amplitude or some causal observable. So the first thing we learned is analyticity. And the second one is crossing. Right? And here I'm going to be very schematic because actually this is not proved rigorously, except in a, but it's physically very robust. You can ask, well, how come this is 0? If I actually ask for the data on here, how is it possible that it's 0? Because if you can actually compute that there's a non-amplitude. So this is my source, this is my response. There's a trivial amplitude for to propagate between S and R. Okay. Actually, this is in Peshkinen's Roy. This is also this famous lecture by Feynman, The Reason for Antiparticles, where he talks about all these things. Right, so this. So what saves us is actually there's also this commutator. One tells you about the kind of probability of a particle propagate from S to R, but there's also probability of an antiparticle. It's also the complex conjugate. The amplitude for an antiparticle from R to S. This is not 0, but actually these things are equal and they cancel precisely for this computer. Okay. When this complex momenta, if the process is related, okay, the process of having a particle come from the state should be related to having R and doing the opposite. And it's called crossing symmetry. So these two things are what we learned from Causality. We actually start to use analyticity today because I can amplitude as functions all outgoing. Okay, since I can any incoming particle, then then my amplitudes will be overlaps of like P1, Pn vacuum because this is related to some process by analytic continuation. Okay, and this I don't need to keep track of what is coming in and what is just the sign of the energy will tell me what is coming in and what is coming out. Okay, I promise it will get more concrete. So today is a lot of these basic things, and let's see how we can use this. Okay, what is the next? I guess locality. What does locality tell us about scattering amplitudes? Does anybody know? So locality tells us that if I have this amplitude, which is a function of momenta, and actually I take the limit when sum over this momenta goes on shell, this amplitude actually will blow up. It will have some sort of singularity. Okay, so for instance, the simplest kind of singularity, let me call this capital P. It can have a pole. With some residue, let me just call it R pole. But this thing has to blow up. Okay, what is that? Why does the amplitude have to blow up? It means that a particle in this scattering process is going on shell in the intermediate state. This means that we actually have two separate scattering processes. Okay, we have some scattering here. So we start with just all the particles scattering. But then when we tune the kinematics, we'll learn that actually there's some sub-process where this subset, which is called all scatter into a new on-shell particle that propagates and then rescatters with the rest of my particles. And this infinity here is the fact that there is an infinite amount of time that can pass between these two processes. Okay, so here, this thing, because of locality, there's some integral over points in space-time. Here, there's another integral. But if you go on shell, basically you have one too many integrals. You can see that you're trying to integrate over a bunch of points, and then in principle there should be some energy somewhere, but that energy, see that there's a pole in that energy already because there's an infinite amount of time, so there's an extra integral over time that is already saturated because you're on shell. Okay, it's satisfied automatically. So if you wish, is the extra delta function that you have.
Wouldn't that require the channel to be a stable particle?
Yes, but in perturbation theory, everything is. Oh yeah, sorry. So the question was, wouldn't that require the channel here to be a stable particle? So if you want to take this kind of very formally and axiomatically, yes, we only talk about scattering of stable particles. It turns out that all of these principles hold in perturbation theory also. And a lot of the things that we'll be doing are in perturbation theory, which is how we usually do computations in wiggly theories. And it's still true that even if you have a particle that would get some width at one loop, at tree level, you will see that it appears in some intermediate channel and it generates a pole. You know that the only thing that will happen is that when you include that width, that pole will move off somewhere out in the complex plane. But there will still be a pole in the amplitude. It just won't be as simple as this. OK, more questions. All right. Same way that there's this pole here that somehow corresponds to having some particle propagating in intermediate state, I can have other types of singularities. So the amplitude can also blow up in different ways. So for instance, I can have a logarithm of p minus 4m squared. And this tells me that there's particle production. This tells me that actually there's some, because I have a process where I produce two particles, that's m. And again, those two particles rescatter, et cetera, et cetera. So locality tells us that the amplitude will have a bunch of singularities, some stronger like poles, some milder like logarithms, but they're going to be there and we should expect them. Okay, so for instance, you can have log p squared minus 9. So this will correspond to now a process where I have 3 particles, or you can have a log squared. So this is something where I have 2 particles that rescatter, and then they rescatter again, et cetera, et cetera. OK, so locality tells us that there have to be a bunch of singularities in these amplitudes. And finally, unitarity actually becomes very powerful in combination with this, because unitarity tells us that actually the residue of each one of these singularities is fixed. So unitarity tells us, for instance, that the residue of this pole actually is a sum over the product of these processes that can happen. Okay, so the singularity that an infinite amount of time can pass, but the coefficient of that thing should be just the amplitude for scattering these things first and those things later. Okay? So it will be a sum over all intermediate states of actually the amplitude for these particles that have momentum p to scatter into some state x times, here I write minus x for kind of the antiparticle of x with the opposite momentum because everything is outgoing. Yeah. And this we'll see tomorrow. Actually, we'll do a bunch of examples of this, and we'll see how it is true, and it's really constraining. It tells us that actually, whenever we have a singularity, a pole, we actually already know what the coefficient is. And typically, these are lower point. Because here, maybe, okay, here I drew a 7-particle scattering, right? But then one side here is a 5-particle process, and this one is a 4-particle process. So you see that there's some piece of the 7-particle amplitude, which I already know it has a pole, and then its residue is fixed in terms of lower point amplitudes. So if I know the lower point amplitudes, I can predict something about the higher point amplitude. Okay, so this means that we'll start with the lowest point amplitudes, 3-point amplitudes, and we'll try to build other things from those. Okay, what about the residue of this log, this 2-particle log? Okay, that one you have to work a bit harder, but again, unitarity tells you that this will be sum over like x1, x2, all possible states. Then you also have some integral over the Lorentz invariant space of these particles, and then the product. So here I'm going to have x1 minus x1, x2 minus x2. So again, the coefficient of the log is fixed by unitarity. So if I have these lower particle amplitudes, I can glue them. I can compute some unitarity cut where I just sum over the phase space and over all of the particles that can cross this thing, all of their helicities, all of their spins, whatever I have in my theory, and that predicts the coefficient of this log. And that will be extremely important when we start talking about RG and all of these things. Yeah?
I did not understand how you got from locality to singularities and amplitudes.
So, yeah, the question is, I didn't understand how you got to singularities in the amplitude from locality. Okay? Just trying to give you an intuitive picture, right? Of course, if you take a local Lagrangian, this thing will just be a propagator that appears, and it tells you that you have a particle propagating from point 1 to point 2.
We don't want to use Lagrangians.
Yeah. So the intuition that I can give you is that everything has to blow up, because an infinite amount of time can pass between these two processes. And the only way it can blow up is if you have a pole, or a log, or the square of a log. So that's the menu of options, and that's what appears. Okay, so of course, you can derive all of these things in perturbation theory from field theory, but here I'm just giving, if you wish, this as an axiom, and I just declare that this is how locality shows up in an amplitude. Is there another question?
Explain the difference between the second and third.
Yeah, so the second here is p squared minus 4m, right? And that's when I have production of a pair of particles whose minimum energy will be 4m squared, which is kind of twice the mass squared, which is just the 2 particles at rest, right? So here there's some branch cut, some singularity, whose branch point is precisely a threshold. This is p minus 9m squared, which is 3m all squared. So here you have 3 particles in the intermediate state. Yeah, there's an r log 3 and an r log squared. So there's always some residue. And the important thing is that those residues are always constrained by unitarity. Okay? And they're given in terms of lower point processes. OK, more questions? Yeah.
Why you need to restrict the factor, this factor r? Why gives you that factor?
Why does it give you that factor? I mean, if you wish, I'm just what was unitarity? Unitarity is probabilities add up to 1. So I just resolve 1 as a sum over everything, some complete set of states. And the statement is that because anything can happen, I scatter this particle here, anything can come out, it can rescatter. I'm just inserting this one and resolving everything that can happen as every possible state that can propagate between kind of first scattering process and the second scattering process. Okay. Now, if you go to some Feynman diagram computation, you will see that there's these completeness relations. Like if you look at the propagator, the numerator, when you go on shell, it can always be written as a sum over polarizations or a sum over spin or something like that. So there's these completeness relations that when you're actually doing a calculation, will enforce this. But here, we're just taking it as given, because I will try not to talk about these wave functions. OK, I have some more questions. Yes?
So can you only get poles in logs, or are there other bigger types of different
So, okay, the question is, can you only get poles and logs, or can you get other weird divergences? Close to the real axis, we can only get poles and logs. If you venture somewhere out in the complex plane, okay, there can be dragons there. So, yeah. So, and what is the coefficient of those? That's actually under current investigation. Actually, since the 60s. So it's not. Yeah, it's been a while. But yeah. But already the fact that we know the coefficients of these poles and these singularities, we can get a lot of mileage out of this. Okay, more questions. I like questions. Yes.
Sorry, it's a stupid notation question. Whatever is in the middle,
Yeah.
is that an ax?
Yeah. Well, this was times. This, yeah, just times. Yeah. Okay. How much time do I have? Half an hour?
Half an hour.
Okay, good. Oh, another question.
I'm a little bit confused that you said it's a type segment. I saw this branch couplet actually before.
Yeah. Well, I mean, sometimes for loops, we draw this as a cut, typically. But what this cut means is I take the two amplitudes, I take their product, and then I integrate, right? Here I'm just saying, okay, I just made the integral explicit, the sum over intermediates is explicit, and this is the product of the amplitudes.
I have a question. When you say analyticity, do you mean is it everything over a complex plane or the real plane, or what you mean?
Yeah, in the complex plane, yeah.
All over the plane?
Yeah, it can be analytical continue to complex values, and then okay, you have to worry about whether you find these other singularities that were just mentioned. But yeah, we believe that the amplitude can be extended to an analytic function for any value of the complex momenta. Just be careful if you encounter a branch cut. Yeah. Okay, so these are the basic principles. Now I'm going to try to actually find some good variables to write these amplitudes, because we want to start using them to write amplitudes. Okay, so I'm going to introduce this called Spinor-helicity, which will make our life much easier. Right? So for now, what we said is the amplitude is a kind of momenta with some representation of the little group. Maybe there's some like UV scale. Maybe there's a bunch of parameters which are dimensionless. I normalize everything by this UV scale. I want to understand the dependence of the amplitudes on these momenta, but these momenta, they're not great because actually they square to m squared, so they're kind of constrained variables. So we want to use slightly better variables. So we're going to exploit the following fact. We're going to exploit the fact that the Lorentz group so SO 3,1 actually can be written as a pair of like SU2s. Let me call this left and right, not to be confused with anything electroweak. And actually, for general complex momenta, these are SL2Z. So what are these things? This is the thing that acts on left-handed Weil spinners. This is the thing that acts on right-handed Weil spinners. Okay. Okay, so we're going to have two kinds of indices, undotted indices, which are like SU2 left, and then dotted indices, which are of SU2 right. Okay, and we have that these guys, if I have some object which has one of these indices, under a Lorentz transformation, it will just act with some matrix M. And similarly, if I have another object which has one of these alpha dot indices, then I will act with basically the adjoint of M. Oops. Okay, why is this useful? So let me define a following matrix, alpha alpha dot, which is just 1, and then the Pauli matrices. And I can just dot my momentum, any momentum with this. So this turns this momentum into some matrix, which is to be concrete in components. This thing is going to look like and now instead of acting with the usual lambda, so when we take some Lorentz transformation in vector notation, now I can write it as a pair of these M matrices. Okay, so in terms of this alpha alpha dot, I'm going to have that this is equivalent on acting on the left-handed Weil spinor and the right-handed Weil spinor separately. Okay, so this will take this P alpha alpha dot to M P M dagger with the appropriate indices. Now, a nice thing about this matrix is that the determinant of this matrix is precisely the mass. You can check that pretty easily just from this. All right. Let's see what we learn about massless particles. So if the determinant equals 0, it's a 2x2 matrix. It has rank 1. Actually, that means I can write it as a product of vectors. So you'll be able to write P as left-handed Weil spinor times a right-handed Weil spinor. Okay, so for momenta, these things are complex conjugate, maybe up to a sign. But in general, for complex momenta, these are two truly independent variables. Okay, what about when M 0? That means that, so here we had rank 1. Here we have that determinant of P is not 0, which means it has full rank. Best I can do is write it as a product of two vectors. Actually, for convenience, use this epsilon ij, which is the usual antisymmetric tensor, and I'm going to write it like this, and you'll see later why. Okay, so just to spell it out, this is lambda alpha 1, lambda alpha tilde 2.
Sometimes your dotted indices are hard to distinguish from non-dotted.
Thank you. Okay, so in this case, this is particularly nice because now these variables are unconstrained. If I write things in terms of these lambda and lambda tildes, this guarantees that the momentum is on shell. So I can choose any pair of these guys, and it will always give me shell momentum. Here, I can choose them. There will be some constraint that it gives them mass. But there's something else nice about these variables, which will allow us to actually make use of what we learned from symmetry. So what we learned from symmetry about the amplitude is that okay, the amplitude is a function of momenta, but it's also some representation of the little group particle. Okay, so it has to transform under the little group for each individual particle. So let's think about the little group for massless particles. For m equals 0. And now we can ask what transformation of these lambdas and lambda tildes can leave p invariant. Okay, so we want to have some m that leave in. To see this is just the product of lambda and lambda tilde. The best that I can do is that I can multiply each one of them by fx. So this thing will transform as t times lambda alpha, and this thing will be t minus 1 and this t is precisely this little group phase that I wrote before. Okay, so what does that tell us about the amplitude? We can write the amplitude for massless particles in terms of these lambdas and lambda tildes. And actually, this amplitude will have some specified homogeneity in each one of these guys, because I remind you that this amplitude is just the overlap of these multi-particle states. We already discussed that the little group just faces each one of those particles, right? So if I actually multiply this by t minus 1, this is doing a little group transformation. So this should come out as a product over each particle, basically t minus 2 hi times the amplitude. Okay, so we'll see tomorrow that this is extremely constraining. This fixes most of the answer. So let me just write in words. Amplitude is a function of Spinor-helicity with specified and the same thing is going to be true for massive particles. It's only slightly more difficult. So let's see if we can recognize the little group for massive particles. So let's do the same exercise. So now we have a little group for massive. Now we want some transformation. M now I have this extra label I, because I had two different vectors, two different spinors. So in general, this is going to be some Lij acting on I. And similarly, I'm going to have that my lambda tilde Okay, so if I want this momentum to be left invariant, what I learned about these matrices here that now carry these indices is that Lij or Li actually, let me lower these indices. So what are the matrices that leave the antisymmetric 2x2 tensor invariant? These are, again, generators of SU2. So we find that indeed, as we predicted, the little group for a massive particle is SU2. It's just SO3, just rotations in the rest frame. Right? And these variables transform nicely under this little group. So this extra index that we need to add, that here is just whatever vector I added to write a matrix of full rank. If I write it in this smart way, it turns out that it's precisely a massive little group index.
Is it I or lambda j on the right-hand side there?
Lambda j, you're right. Thanks. Yeah. I'm also not being super careful about upper indices and lower indices because I can raise them and lower them again with this antisymmetric tensor. Okay? So forgive me. Okay. So what's the analog of this?
I think there's a question.
Oh, yeah.
You can raise and lower also the half and half adult.
Yes.
Similar axis.
Yeah, I will talk about that in a second because we'll actually use it. Yeah. Okay, so now amplitudes had to carry some representation of this little group. So what we learn is that the amplitudes for massive particles, which are a function of this massive spinors, actually they will carry a bunch of these indices, right? So this will have like I1, I2 spin of the first particle. If there's some other particle, then there will be, okay, let me just write one. Just as an example. So if we have a particle of spin S, then we'll have which are carried by these variables too. Okay, so these variables let us precisely understand how the amplitude transforms the little group, and we'll be able to do it just in terms of these variables, which capture both the momentum of the particle and the little group properties. Okay. Okay, so just to wrap up with symmetry, so same thing here. So, okay, amplitudes are functions of Spinor-helicity variables which carry here a representation of this SU2 massive little group. I think I had some exercise somewhere here. Let me check. Oh, it's coming.
Now, ask about the notation for the equation there.
This one here? Yeah. Yeah, so here I have product over all i's, and this is the same factor to the power minus 2 times the helicity of particle I. Yeah.
Sorry, but because I on the left-hand side is specific. Oh, the left-hand side.
Yeah, so this just denotes all of the particles, right? Here I have many different i's, but I'm rescaling each one of them same factor. So lambda 1, I'm rescaling by t, lambda 2, I'm rescaling by t, et cetera, et cetera.
Does it confuse like the right-hand side is W variable to do the pronoun on the left-hand side?
Yeah, well, I'm not sure which better way to write it, but there's some prefactor here, right? This is a function of the Spinor-helicity of each particle, right? And when I rescale all of them by t, I find that I get the amplitude again, which is still a function of those guys, multiplied by some phase, which depends on the helicity of each one of the particles. So this is some prefactor.
Product J and the thing in the exponent J.
Yeah, okay. Yeah, maybe that's better. Not that my i's and j's are very different. But.
That's another question.
Oh, yeah.
Can you just clarify what are the indices of that parenthesis for?
Yes, so
The lambdas?
yeah, so the lambdas, each one of them carries one SU2 little group index, right? The amplitude, because it's an overlap between multi-particle states, for each particle has to carry a representation of the little group, so we'll have to carry 2s indices, right? But the important fact here is that because we have objects that carry these indices, we just need these variables. And we can always write a prefactor. For instance, I could always write, say, only the first particle has spin 2, right? I know that I can write the amplitude as follows. I could write it as lambda 1, I1, lambda 1, I2, lambda 1, I3, lambda 1, I4, right? So this is 2s, if it's 2, symmetric minus the trace, and then now some function where all of those indices are contracted. Always carry the little group representation using these variables. So this is just to say that these are all the things I need to write the amplitude. Okay, and the last thing I want to do today is to just write the other symmetry generators in terms of these particles, because we'll learn one more thing. Do it for the massless case, and then you'll have to do it for the massive case, because I won't have time. So let's go back to this Poincaré. Algebra for massless particles. Right? So what is the generator of momentum? If I have n particles, this is going to be the sum over each one of those particles, the I alpha. Okay, so my momentum generator is just P, which is the sum over all of these guys. Yes?
Question. So you derive the result for massless particles
Yeah.
and one for massive.
Yeah.
Okay. But if you have a process that includes both, then is there a generalization or?
Yes, of course. You would just have that in the massless spinors, it will have to have the fixed homogeneity, and then it will have to carry the right indices for the massive particles.
So just a combination.
Yeah, that's right. Yeah. Yeah, the question was, what happens when you have both massless and massive particles? Okay, so the moment generator. What about the angular momentum? So we're going to have alpha beta, which is going to be lambda alpha And similarly for okay, so exercise. Check the algebra to check that these things have the right commutation relations. Okay, so let's just impose translation invariance and rotational invariance on the amplitude. So the first one is going to be that P acting on the amplitude is 0. How is that possible? This is just a number that I'm multiplying the amplitude by. The only way that this is possible is if the amplitude is proportional to a momentum conserving delta function. What about these other guys? What about J acting on the amplitude equals 0? Okay, that's more tricky because this operation acts on spinors. Anything with this form, and there is rotations. But back to what Sam was asking, there's this extra object that we haven't used yet, which is an invariant of the SU2 left or the SU2 right. We have this, again, antisymmetric tensor and these alpha beta indices. We can construct the following combinations. So let me denote this by angle bracket ij. And you can check yeah, but here I forgot that I also need to sum over all particles, of course. So there's a bunch of check that this J annihilates each one of these. So what we learned from this, the same way that from rotation, translation invariance, we just learned that the amplitude has to have a delta function. From this, we learned that the amplitude, which we thought was just a combination of these guys in any form, actually can only depend on that delta function. It can only these combinations, ij. And there's an analog for j tilde, where we now put dots here everywhere, and I call this bracket, square bracket, sorry. And then again, you can check that tilde acting on this thing equals 0. Technically here, there's some mention, there's some sign that you might have to check, but okay, so let me just make, okay, I will make more comments about these guys tomorrow. They actually are. But what we learned is that the amplitude is actually a function of these particular contractions between the spinors. Yes?
Is this just a fancy way of saying it only depends on like relative momenta? Or is it more than that?
It's more than that, because it's actually transformed under the little group. Yeah, the question is this just a fancy way to say that they only depend on relative momenta or square of relative momenta, things like that? No, it's more than that, because these things still transform under the little group of each particle. Yeah. Okay, I have 0 minutes, right? Okay.
Yeah, -0.5.
-0.5, okay. So I'm just going to take a credit. Yeah, I'm going to switch the signature, so I have +5.
Remember, we've been here for many hours.
Yeah. No, I just want to make one more comment, which is that using these variables, I can also write the generator of helicity, which is just lambda I dd. So this is for each particle minus lambda tilde and then the dilatation operator, which in general is not a symmetry, is the same thing but with a plus sign, right? And then the other two things that I know about the amplitude is that we said it has, so this is for massless particles, it has specified homogeneity, so I know that if I act with the amplitude on the amplitude with this guy, I will have minus 2 hi times the amplitude. And then if I act with the dilatation operator, so we want to do dimensional analysis, so this will be useful. This will be 4 minus n, where n is the number of particles, times a. Okay. So, okay, I'll summarize at the beginning of next lecture, but essentially we've found